Hey everybody, hope you are all doing well. Today's lesson is on fractional exponents and radicals. Now, we have gone through a bunch of exponent laws, and then we took a break and we talked about radicals. We talked about what the difference is between a mixed radical and an entire radical, how to go from mixed to entire, and then also, which is probably more important, how to go from entire or mixed to a simplified version, which meant that the number as the radicand was as small as possible. That's what you end up doing more of in this course, is simplifying radicals. You do that more than you would go from mixed to entire. So now, today we're going to introduce one of two brand new exponential laws that you haven't talked about in junior high, okay? Today is on fractional exponents, and tomorrow will be on negative exponents, and then that's gonna kind of wrap up this unit for us. Okay, but before we do that, let's just quickly review. I want you to completely simplify the following. So we're looking at 2 root 98. I would love it if you paused me and just tried these three by yourself first, and then come back and take a look at my answers, okay? Remember, you're looking for a perfect square factor of 98. That one happens to be 49. So we break the 98 into 49 times 2. And then the root of 49 is 7. So then the 7 times 2 is what gives me the 14 that you see there. Okay, again, because this is just a quick review, I'm just throwing answers at you. I would totally want you to show me the work that you just did. Okay, for the next guy, 3 root 288. I see that as 3 times root 144 times 2, 144 times 2, sorry, root of 144 times root of 2. 144 times 2 gives me that 288. The root of 144 is 12. So we'd be looking at 12 times 3 on the outside, which is 36, and root 2. And then for the 5 cubed root 81, I need a perfect cube. That's a factor of 81, which happens to be 27. So I'd be looking at 5 times the cubed root of 27 times the cubed root of 3. And then the cubed root of 27 is 3. So we'd be looking at 5 times 3 on the outside, which is 15. So final answer would be 15 cubed root 3. Okay, the next thing we have to talk about is we need to do a quick review of some fraction rules. Make sure you're comfortable with math operations on fractions. So when we're adding fractions together, we need to have a common denominator. Once we have a common denominator, we're just adding the numerator. So if you look at this first example, we already have a common denominator here with the 2. So we're just gonna add the 1 plus 3. 1 plus 3 is 4. So I'd be looking at 4 over 2. And then remember that fractions are division statements as well. 4 over 2 means 4 divided by 2. Well, I know what that is. 4 divided by 2 is just 2. So I would simplify that to just the whole number 2. If I looked down here, I don't have a common denominator. So the first thing I would need to do is get a common denominator. In this instance, it would be 6. So we would want to rewrite this statement with equivalent fractions that have a 6 on the bottom. Okay, so 1 over 3, I would write as 2 over 6. Remember, whatever you do to the bottom, you have to do to the top. So if my 3 turns into a 6, that's because I multiplied it by 2, so I do the same thing to the 1. The 1/2, as an equivalent fraction over 6, that would be 3 over 6. So I have changed this to be 2 over 6 minus 3 over 6. Once I have a common denominator, I just add or subtract the numerator. So 2 minus 3 is negative 1. So my final answer would be negative 1 over 6. Okay. 15 and 20 over here. Now you could find a common denominator by multiplying 15 times 20. That's a fairly large number, and there's a smaller one that you could use. It's not wrong to just always go the 2 multiplied together. It's just sometimes it makes your life a little bit more complicated because you're dealing with such large numbers. When I see 15 and 20, I want to change those both to be 60. I can change 15 to 60 by multiplying by 4. And I can change 20 to 60 by multiplying by 3. Again, whatever you do to the bottom, you have to do to the top. So my 11 turned into a 44 because I had multiplied the 15 by 4. And my 3 up here turned into a 9 because I had to multiply that 20 by 9. Now that I have a common denominator, I subtract the numerators. That gave me 35 over 60. And now I always want to have my answer reduced. So 35 and 60, both of those are divisible by 5. And so I reduce it to 7 over 12. Okay. When multiplying fractions, we just multiply the tops, multiply the bottoms. Okay. So 1 times 3 is 3, 2 times 5 is 10. So that leaves me with 3 over 10. I don't know if this was ever talked to you before or not. But if we took a look at this guy here, one of the things you can do with fractions is you can, before you do the multiplication, like you could go 12 times 15 right now. That's totally fine if you want to do that. But you can reduce the top and the bottom, even if they're not on the same fraction, as long as everything is multiplication. So I look at 12 over 4, and I'm just going to say, hey, I'm going to write that as 3 over 1. Okay, I just divided a 4 out of both of those terms. 15 out of over 25, I can take out a 5 there, so I'm going to be looking at 3 over 5. And then my numbers are way smaller. I didn't need to go grab a calculator for any of this. 3 times 3 is 9. 5 times 1 is 5. So I'd be looking at 9 over 5. Now, some of you may say that's not right because I have to put it into a mixed number. And if you want to put it into a mixed number, that's fine. But 9 over 5 is perfectly acceptable. It's okay to have your answer as an improper fraction as long as it's reduced, okay? If you want to write it as a mixed number, you can also do that. That's 1 and 4 over 5, okay? All right, and then division of fractions. There's actually 2 different ways to divide by fractions. One is to get a common denominator. So you could look at this guy and the common denominator would be 10. So I would write it as 5 over 10 divided by 6 over 10. And then once you have a common denominator, you just actually divide the numerators. So that would end up being 5 over 6. The other way to do it, which is probably the way you're more used to, is to change the division statement to multiplication. And we say flip the second fraction, but you would, division of a number is the same as multiplication of that number's reciprocal. The word reciprocal there refers to flipping it. The bottom becomes the top becomes the bottom. You're only doing that to the second fraction though, not the first. So here's my example of a common denominator. Once you have a common denominator, you just divide the numerators. And then here's my example of writing it as multiplication and flipping that second fraction. Either way, you get the same answer, 5 over 6, okay? All right, so you give this a shot. Okay, some of you may have seen this and said, okay, I have to do the 1 plus 3, so that's 4. 4 divided by 4 is actually 1, so that's gone, and I'm left with 7 over 2. The answer is 7 over 2 or 3.5, however you'd like to do that. Okay? All right, now let's get on to what we actually want to learn today. An exponent tells you how many times to multiply the base of a power by itself. The number 4 to the 3 tells you tells you to multiply 4 by itself 3 times. I would want those 2 statements to feel very, very familiar to you at this stage of the game. Okay? Nothing there should sound out of the ordinary. This one might sound a little bit more complicated though. In the same way, 4 to the 1/2 tells us to multiply 4 by itself half of the time. And what we got to try and do today is just kind of figure out what that means. Okay, so I want you to grab your calculator, and if x is 1, I want you to figure out what x to the 1/2 is. So essentially, I want you to take what 1 to the 1/2 is, okay, and then 4 to the 1/2, and then 9 to the 1/2. If you have a calculator where when you press the exponent button, it opens up a little box like that, then up there you could just write 1 divided by 2, or you could write 0.5. Okay, if you're going to do the the 0.5 thing, if you're going to do the 1 over 2 thing, and you don't have that little box appear, what you would need to do, like if all you see is this, what you would need to do is then open up a bracket and go 1 divided by 2 that way. Okay, just make sure that the 1/2 is in its own set of brackets if it's not inside the little box. Okay, so go ahead and fill this out for 1/2, x to the 1/2, and also while you're at it, fill it out for x to the 1/3 on the other side. Okay, so for x to the 1/2, for 1 you should have gotten 1, 4 to the 1/2 is 2, 9 to the 1/2 is 3, 16 to the 1/2 is 4, 25 to the 1/2 is 5. Now what should you be noticing there? You should be noticing that these numbers are actually the square roots of these numbers. Okay, so taking something to the half seems to be the same as taking the square root. Let's go over to the other table. 1 to the 1/3 was 1, 8 to the 1/3 is 2, 27 to the 1/3 is 3, 64 to the 1/3 is 4, 125 to the 1/3 is 5. What's happening there? It seems like taking something to the 1/3 is the same as taking its cube root. On that note, I want you to try and fill out the next 3 rows of these tables. So pause me and do that. And then this is what you should have gotten. So 36 to the 1/2 is 6, 49 to the 1/2 is 7, 64 to the 1/2 is 8. So hopefully this is confirming that taking something to the exponent of a half is the same as taking the square root. On the other side, 216, the 216 to the 1/3 is 6, 345 to the 1/3 is 7, sorry, 343 to the 1/3 is 7, and 512 to the 1/3 is 8. So what do you notice? The numbers in the first column of each table represent perfect squares or cubes, respectively. The second column is the square root or the cube root of the first column, respectively. An exponent of 1/2 seems to be the square root, and an exponent of 1/3 seems to be the cube root. So what do you think the exponent 1/2 means? Well, we just said that an exponent of 1/2 is the same as the square root, and an exponent of 1/3 is the same as a cube root. Okay? So, what do you think a to the 1/4 means, and what do you think a to the 1/5 means? Well, probably a to the 1/4 means the 4th root of something, and a to the 1/5 means the 5th root of something. Okay, if you want to check that out, think about a perfect 4th number. So how about 16? 2 to the 4 is 16. So if you took the 4th root of 16, you would get 2. So go 16 exponent 1/4 and see if you get 2. Okay. 3 to the 4 is 81. You could try that guy as well. So if you took 81 to the 1/4, you should get back to 3. Okay. Let's pick on 1/5 for a sec. 2 to the 5 is 32. So if you took 32 and took it to the 1/5, you should get back to 2. 3 to the 5 is 243. So if you wanted to take 243 and take it to the 1/5, you should get back to 3. Okay. So what does a to the 1/n mean? What we're trying to show you here is when you have a fractional exponent, the denominator of the fraction becomes your root index. Okay, the denominator becomes the root index of the radical. Okay, so what happens when we multiply powers of the same bases? Well, when we multiply powers of the same base, we add the exponent. So this would become a to the m plus n. So what if the exponents were fractional? Well, we do the same thing. We would just add the exponents, 1/2 plus 1/2. Okay. How is the result similar to root 5 times root 5? Well, we've already discussed that root 5 is 5 to the 1/2. And we've already discussed that root 5 times root 5 gives me just 5, right? So I want to unpack a couple things here. Root 5 times root 5 gives me root 25, but root 25 is just 5. Okay, but we've already established that these things here are the same, right? 5 to the 1/2 is root 5. So when I take root 5 times root 5, and that ends up being 5, taking 5 to the 1/2 times 5 to the 1/2 ends up being 5 as well. Okay? Now, why am I saying this? Well, because we want you to think about, in a minute, we're going to change what the numerator is, okay, on these fractions, and we want to think about what that change in the numerator is going to be. Okay, so let's keep going here. So, does 5 to 1/5 equal root 5? Sure it does. What about 5 to the 1/3 times 5 to the 1/3 times 5 to the 1/3 equaling the cubed root of 125? Is this statement true? Yes. Okay. So the law so far for rational exponents with a numerator of 1 is when n is a natural number and x is a rational number, x to the 1 over n will equal the nth root of x. So the denominator of my fractional exponent becomes the root index of the radical. So evaluate without a calculator. 64 to the 1/3, that would be considered the cube root of 64, which would be 4. 0.36 to the 1/2, that would be the square root of 0.36, that would be 0.6. Negative 27 to the 1 over 3, that would be the cube root of negative 27, which would be negative 3. And then 9 over 16 to the 1/2, that would be the square root of 9 over 16, which would be the same as the root of 9 over the root of 16. Okay, so that would be 3 over 4. Okay, so think about it. We're gonna kind of unpack this a little bit more. Can a fraction be written as a decimal? Well, sure it can. 1/5 is the same as 0.2. Well, can a decimal be written as a fraction? Yes, we know how to do that, okay? So 0.4 would equal 2 over 5. Now, why am I doing this to you? Because what if you had to evaluate 32 to the 0.2? Well, what I need you to see is, if we're gonna evaluate 32 to the 0.2, I wanna think about 0.2 as a fraction, because if it was a fractional exponent, now I know what to do with it. So 0.2 as a fraction is 1 over 5. And now that I've written it as 1 over 5, I know, hey, that is the 5th root of 32, which is 2, okay? All right, so can 2 over 3 be written as a product of two rational numbers? Well, 2 over 3 equals 2 times 1/3. Do you agree? Nothing strange there. So how can we evaluate 8 to the 2 over 3 without a calculator? Well, what I want you to see is that would be 8 to the 1/3 times 8 to the 1/3, right? Because when we are multiplying powers of the same base, we could add the exponents together, so that would give me 8 to the 2 over 3. Okay. Well, that would be 8 to the 1/3 times 2, because 2 times 1/3 is 2 over 3, right? So what we do, well, why did I change this to a power of a power? Because I know that I could multiply those together, right? Remember all the exponent rules you already know. 2 times 1 over 3 is the same as saying 1 over 3 plus 1 over 3, right? So this and this say the same thing, okay? Now, we've already discussed that 8 to the 1 over 3 is the same as the cube root of 8. So where am I going with all of this? What I want you to see is if we were to evaluate 8 to the 2 over 3, the bottom of the fraction still became the root index, just like it did in all those slides beforehand. But the top of the fraction actually just becomes an exponent on the whole number. Okay, that's what I want you to see there. So here's the whole thing, the law for rational exponents, x to the m over n. Now look at what I've done. Okay, again, the bottom becomes the root index, and the top becomes an additional exponent, okay? Now, I took you there in a couple of steps because I said x to the m over n is the same as x to the 1 over n to the m, okay? I just split that up to be a power of a power. And then here we're saying, all we're saying here is that it doesn't really matter where that m is. Either you can take it on the whole thing after you take the root, or you could put it on the base and then take the root of that number, okay? This one is probably the easier one to deal with because you're dealing with smaller numbers if you take the root first and then apply the exponent, whereas this one you would be dealing with a larger number because you would take the exponent, you would take the number to the exponent and then apply the root, okay? All right, so write 15 to the 2 over 3 in radical form in two ways. Well, I know that the bottom 3, that's going to be my root index, so that'd be the cubed root of 15. So either I would say the cubed root of 15 all to the 2, or the cubed root of 15 squared. Write the cubed root of 5 squared and the fourth root of 7 all to the 3 in exponential form. Well, the root index becomes the bottom of the fraction, and then the other exponent is the top of the fraction. So this would be 5 to the 2 over 3. And then this guy, the denominator of my rational fraction, my rational exponent is the root index, so that would be a 4. And then the 3 would appear as the numerator, so that'd be 7 to the 3 over 4. Okay, so evaluate without a calculator. Well, I'm going to take the cube root of 27 first, and then I'll take that to the 4. So the cube root of 27 is 3, and then 3 to the 4 is 81. Okay, I need to see you transform this to this first, because I'm trying to see that you understand this exponent law. Okay, I get that you can take 27 to the 4 over 3, just plug it in your calculator and get 81. And if you want to do that to check your work, that's awesome. But you have to show me the intermediate steps so that I know you understand what your calculator is doing. Okay, I need to know that you understand the exponent law itself. So I need to see you do this conversion from here to here before you can go any further. Okay, 0.04 to the 3 over 2. So you could look at that as 4 over 100 if you wanted. Change that 0.04 to 4 over 100. Okay, let's just do that together for a sec, because then that becomes super easy. If I took 4 over 100, I now need to take the square root of that, because that's what the 2 on the bottom is for, and then I'm going to take it to the 3. Okay, so the square root of 4 over 100 is 2 over 10. Then I could even reduce that if you wanted, right? I could have reduced it here to 4 over 100 reduces to 1 over 25. Do you want to do that first? I'm cool with that. 1 over 25. Okay, so then the square root of 1 over 25 becomes 1 over 5, and then I would take that to the cube, so that'd be 1 over 125 altogether. Okay. And then the last example on this guy is negative 32 to the 0.4. Again, we've talked about that 0.4. We'd want to switch that to a fraction. So 0.4 would be 4 over 10, which would reduce to 2 over 5. So when that's 2 over 5, the denominator was 5, so that's my root index. When I switch it to a radical, and then the numerator was 2, so that becomes an exponent on the overall number. The fifth root of negative 32 would be negative 2. And then negative 2 all squared would give me a positive 4. Okay. Negative 32 to the 0.4. Now that's still, this is still to the 4 over 10, which would reduce to 2 over 5, very similar to the last question we did. The difference here, though, is the negative is not part of this conversation right now. Remember that an exponent only applies to what's directly in front of it. So what you need to see there is more like this. That negative is just on the outside, and I'll apply the negative later at the very end. Okay, so it's going to look like this, and then the fifth root of 32 is 2, and 2 squared is 4, but then overall this time my answer is going to be negative 4. Okay, 27 over 8 to the 2 over 3. I'm looking at the cubed root of 27 over 8. So the cube root of 27 is 3, and the cube root of 8 is 2. So I'm looking at 3 over 2, and then that's all squared because of the numerator in my fractional exponent. The numerator is just an overall fraction. So I'm looking at 3 over 2 squared, which would be 9 over 4 as my final answer. Okay, and then 9 over 4, I'm going to take the square root of 9 over 4 because of the denominator here in my fractional exponent. So that'd be 3 over 2, and then I'm going to take that to the 3, so that would give me 27 over 8. Okay, good job. All right, so in your answers above, what's the difference between negative 32 to the 0.4 and negative 32 to the 0.4? We talked about that. One includes the negative in the even exponent and the other does not. So in this guy, your answer ended up being positive, but in this guy, your answer ended up being negative. What is more efficient method when evaluating the above questions, taking the root first or raising it to the power first? And I kind of already explained that. Again, it doesn't matter. It's whatever you prefer. But taking the root first allows you to deal with smaller numbers before you have to deal with the power. Okay? Awesome. All right, so go ahead and evaluate these guys. You can pause me and try them yourself. So I'm looking at the fourth root of 625. The fourth root of 625 is 5. Here I'm looking at the square root of 25, and then I'm going to cube it. So that would be 5 cubed, which is 125. And here I'm looking at the cubed root of negative 27, which is negative 3. And then I'm going to take that to the 4. The negative is inside the brackets here, so it does apply to the even root, sorry, to the even exponent. So that's going to be a positive 81. Okay, negative 3 all to the 4 would give me a positive 81. Okay, 8 to the 5 over 3. Well, I'm looking at the cubed root of 8 all to the 5. So the cubed root of 8 is 2. 2 to the 5 is 32. Here, I'm looking at the square root of 4 over 25, and then I'll take that to the 3. So the square root of 4 over 25 is 2 over 5. 2 to the 3 is 8, and 5 to the 3 is 125. So my final answer would be 8 over 125. And then here, I'm taking the cube root first. So the cube root of 64 is 4. The cube root of 27 is 3. So I'm looking at 4 over 3, and then I'm squaring that. So that would be 16 over 9. Okay. All right. We're going to end with just a little application problem, a little word problem. Coffee, tea, chocolate, and energy drinks all contain caffeine. The equation A equals P times 0.87 to the T represents the percent of caffeine left in your body T hours after you drink a caffeine beverage, where P is the initial amount of caffeine and A is the final amount of caffeine. It's important when you get a question like this that's so wordy, you don't want to shut down, okay? Lots of us just see a bunch of words and say, oh, this must be too hard because there's a bunch of words. It's not hard, okay? What they're doing is they're defining what each one of those letters mean, and then in every equation, essentially, they're going to give you all the information for all the letters but one, and then you have to solve for the one they haven't given you. That's what really every word problem is, okay? You decide to drink a Red Bull at 10 p.m. to help you stay awake to study. Red Bull contains 80 milligrams of caffeine. How much is in your system at 6:30 a.m. when it's time to get up for school, which is 8.5 hours. So 8.5 hours, that's your T value, okay? We know that you started with 80 milligrams of caffeine, okay? So would that be P or would that be A? Well, P is the initial amount and A is the final amount. So 80 milligrams of caffeine, that's your P value, okay? So you know a P value and you know a T value, so you're just gonna plug it in your calculator now and figure out what the A value is, okay? So there's my P value, there's my T value, plug this in my calculator, and I can just do this in one step. If you have a graphing calculator, just go 80 times 0.87 to the exponent of 8.5, and you're gonna get that there's 24.5 milligrams of caffeine left in your system, okay? I would also wager to guess that you did not get a good night's sleep that night. Too much caffeine running in your body. All right, so that's it for this guy. And we will talk again when we deal with negative exponents. In the meantime, try your homework and come see me with any questions that you have. Have a great day, guys.